Today, we are going to take you on a fascinating journey into the world of plasma, the fourth state of matter, through our project Plasma Generator, a high energy ionized gas system. Our goal is simple to show you how we built a low cost, low discharge plasma device and explain why plasma is so important for the future of science and technology. This presentation details the development of a low-cost plasma generator that we designed and built using a high-voltage inverter and a modified Tesla coil. Unlike costly commercial systems, our setup reduces stable glow discharges in different gases, including argon, helium, and even atmospheric air. To confirm successful plasma generation, we carried out diagnostics such as voltage current or VI curves and emission spectroscopy. These measurements gave us clear evidence of plasma formation and helped us understand its behavior. But before we go, let's talk about plasma itself. Plasma is often called the fourth state of matter. Alongside solids, liquids, and gases, it forms when a gas becomes so energized that its atoms split into ions and electrons, creating a glowing, conductive state. Plasma isn't just a scientific curiosity, it is absolutely crucial in modern technology. For example, in electronics, plasma is used for etching and cleaning semiconductor circuits. In advanced propulsion systems, plasma thrusters power satellites and spacecraft. And in sterilization technologies, plasma can destroy harmful bacteria and viruses without using chemicals. So our work doesn't just stop at building a device, it contributes to understanding a technology that powers everything from space exploration to medical science. In short, this project combines innovation and accessibility by using simple components like a Tesla coil and inverter. We created a robust plasma platform that can be studied, tested, and applied without the prohibitive cost of commercial devices. To begin with, let's define the problem statement. Commercial plasma devices are prohibitively expensive, which severely limits access for academic research and small-scale industrial applications. This high cost creates a significant barrier to entry for innovation, preventing students, researchers, and smaller organizations from exploring the vast potential of plasma technologies. In contrast, our project aims to remove this barrier by developing a low-cost alternative that still delivers reliable plasma generation for experiments and demonstrations. This brings us to the research need. There is a critical need for an affordable, flexible, and laboratory-scale plasma system that can be used for educational and experimental purposes. Commercial devices are excellent for industry, but they are often too costly, bulky, and complex for classroom and laboratory level research. Our plasma generator fills this gap by providing a practical low-cost platform to study plasma without the need for industrial budgets. Based on this, our project had three key objectives. First, HV module integration to utilize a high voltage inverter and modified Tesla coil modules as the core of the design. These components are cost effective yet capable of producing the required voltages for plasma initiation. Second, stable plasma generation. To achieve consistent glow discharges in multiple gases, specifically argon, helium, and even air, this demonstrates the versatility of our setup compared to commercial units that may require specialized gases. Third, parametric study. To investigate how voltage, pressure, and gas type affect plasma characteristics. This is important because it not only validates the device scientifically but also creates opportunities for hands-on experimentation in classroom and laboratories. Together, these objectives ensure that our plasma generator is not just a low-cost prototype but a scientifically valuable tool for education and research. So, by addressing the problem of high cost, fulfilling the research need for accessibility and achieving these objectives, Our project proves that plasma science doesn't have to be locked away in expensive lab with the right design. It can be studied and explored by anyone anywhere. Let's start with the key applications of our plasma generator and why it can be more effective than commercial alternatives. 1. Surface treatment. Enhancing material properties. Plasma can modify the surface of materials, improving adhesion, hardness, and resistance, while commercial plasma systems for this are often large and expensive. Our device demonstrates the same fundamental process in a compact and affordable setup, making surface treatment experiment more accessible for labs and students. Second, plasma pyrolysis, waste treatment and gasification. Plasma is used for waste treatment, breaking down complex materials into useful gases for energy recovery. Industrial systems cost huge amounts to install and maintain. Our plasma generator, although smaller in scale, shows how the same principle can be achieved with a low-cost design, making it ideal for educational demonstrations of waste to energy technology. Third, ion thrusters, spacecraft propulsion. Ion thrusters use plasma for high efficient propulsion in satellites. Commercial ion thruster systems are incredibly expensive and complex. Our plasma generator, while not built for actual space use, provides a working model that simulates ionized gas flows at a fraction of the cost. This makes it an excellent tool for research, teaching, and proof of concept projects. Fourth, sterilization, medical applications. Plasma is also used for low temperature sterilization of medical instruments. Unlike commercial sterilizers that can cost thousands or millions, our device can produce stable plasma discharges in multiple gases, showing how sterilization works in principle against at a significantly reduced cost. Our plasma generator design also has several advantages that make it stand out compared to commercially available systems. First, modular design. The components are easily replaceable, meaning maintenance is simple and cost effective. Commercial devices often require expensive servicing or replacements. Second, multi-gas capability. Our system operates with argon, helium, and even air, while commercial devices may require specialized gas feeds, increasing costs. Third, cost effective. Perhaps the most important factor, our plasma generator achieves stable glow discharges at a significant cost reduction compared to commercial units while still being highly effective for demonstrations and small-scale experiments. Of course, no device is without its limitations and hazards. We need to acknowledge them for safe operations. First, cathode erosion. Over time, the cathode wears out and needs periodic replacement. This is common in all plasma systems, but easier to manage in our modular design. Second, UV hazard. Plasma emits ultraviolet light, so operator must wear protective eyewear during experiments. Third, high voltage insulation. Our device works with a high voltage circuits, so careful isolation and proper insulation are absolutely essential to ensure safety. Compared to commercial systems which have inbuilt safety enclosures, our device requires greater operator awareness and adherence to safety protocol. So, in summary, while commercial plasma generators are powerful and industrial grade, our low cost design provides accessibility, flexibility, and affordability. It may not replace large scale industrial units, but it opens the door for education, research, and innovation at a fraction of the price. Now, let's look at the future enhancements of our plasma generator and how these upgrades can make it even more effective than current commercial operations options. First, IoT integration, real-time monitoring and control. In the future, we aim to add IoT-based monitoring and control. This would allow users to track plasma conditions and adjust parameters remotely through a web interface. While commercial units already have advanced control systems, they are expensive. By integrating IoT into our low-cost setup, we can provide similar functionality at a fraction of the cost, making it highly valuable for educational institutions and small lab. Second, RF upgrade, radio frequency power supplies. Another planned enhancement is upgrading to radio frequency power supplies. RF plasma have broader applications, especially in semiconductors, coatings, and material processing. Commercial RF plasma systems are extremely costly, but our modular design allows us to explore this technology in a cost-effective and customizable way. Third, portable sterilizers, compact and handheld design. Finally, we envision developing a portable plasma sterilizer, a compact handheld device for on-site sterilization of medical tools, surfaces, or even field equipments. Commercial sterilizers are often bulky and expensive, but a prototype version based on our design would provide a low-cost mobile alternative with practical benefits in healthcare and emergency situations. In conclusion, we have successfully developed a low-cost plasma generator capable of producing stable glow discharges in multiple gases, including argon, helium, and air. Our system has also verified Paschen scaling, proving that it operates on solid physical principles and provides a robust, reliable platform for laboratory research. Compared to expensive commercial plasma devices, our design demonstrates that it's possible to achieve practical plasma generation at a fraction of the cost, making it an excellent tool for educational demonstrations, proof of concept research, and small scale experiments. In short, our plasma generator is more than just a device, it's a gateway to understanding plasma science and and an affordable step towards the future innovations. This brings us to the end of our presentation on the plasma generator, a high energy ionized gas system. We'd like to sincerely thank you for watching and showing interest in our work. This project was not only about building a device but also about learning, experimenting, and sharing knowledge about plasma, the fourth state of matter. If you enjoyed this presentation, don't forget to like, share, and subscribe to support our journey. And if you have any questions, ideas, or feedback, please free to drop them in the comments. We'd love to hear from you. Once again, thank you for your time and attention. This is Team Plasma signing off.